Okay, so basically the plan for today is to cover 15.3 double integrals in polar coordinates, and for the supplements, 15.4 and 15.5 later this week. And then 15.6 will kick to next week. And next week we'll cover 15.6 through 15.9. So uh, just pushing a little bit of that extra work to next week because we lost Monday's class. And then just a reminder, the midterm exam is this week. So it's due Sunday at 11:59 p.m. I see that several people have already completed the exam, so great. Please don't wait until the last day or even the last couple of days to plan to start the exam. It is worth a significant portion of the grade, and you really don't want to miss it. There are no due date extensions, so make sure that you give yourself a buffer just in case a technical issue or something like that were to pop up. And again, the Examity practice exam is posted. I would strongly recommend completing that well before the actual exam. Just in case any tech issues pop up, you can make sure to take care of those and still give yourself a nice buffer for the midterm. And as I kind of already mentioned, the sample exam is also posted. So does anybody have any questions on the midterm or anything on the administrative side of things? Okay, so then let's jump into the material. All right, so moving on to double integrals in polar coordinates, and we'll start with just an introduction to the basic idea and essentially the definition of what we're working with here. So just recall, in rectangular coordinates, question in chat. Yeah, so before we jump into this question in chat, I think it's important to address. There are kind of like two pre-exam things. The Examity practice exam is only really meant to practice the Examity side of things. It has 4 or 5 dummy questions in there just as something to be in the exam, but that's not going to be like the midterm exam. But the Examity setup from the Examity practice exam is what will be like the midterm exam. So the Examity practice exam is to get you logged onto Examity, to get the browser extension installed, to make sure that you understand how to start a session on Examity, how to get the password entered from Examity into WebAssign, all of that kind of stuff to get the test up and running. That's what the Examity practice exam is for. The sample exam, which I know it's similarly named, the sample exam is what's like the midterm exam. So this is the material preparation, and this is the administrative preparation. So the Examity practice exam is to get all those administrative details worked out in a lower stress environment, so you're not worrying about how do I get all the sessions started up and all that, while you're also already a little bit stressed with getting ready to take the midterm exam. And the sample exam is not password protected. You don't take it through Examity. It's just posted and available. You can open it up just like any other homework, and it is the review for the material, the actual calculus material. Like I said, there are a couple of calc problems in the Examity practice exam, but they're just there just kind of to have something there so you can click around and you can submit things in that environment and make sure everything works. But really the material review and preparation is the sample exam. The Examity practice exam is to practice the administrative side of things, and the material that's in there is just filler. Okay, so just recall that a rectangle in rectangular coordinates looks something like this. It's the set of all x and y such that, well, we have x between a and b, and y between C and D. So I can pick x freely any way that I want between A and B, and I can pick y freely and independently of x anywhere between C and D. Importantly, this is a rectangle. I mean, this kind of obvious, but something like this is not a rectangle. Even though in some sense, kind of x could take on values anywhere from A to B and y could take on values anywhere from C to D, well, my choice of x restricts my options for y or vice versa. So if I pick x a certain way, I can't freely pick y to be any number between C and D and vice versa. So just because one variable can in some cases go, say, as low as A or as high as B, and that can be said for the other variable as well, there's an important idea of independence here. I could pick x any way that I want, and regardless of what I pick for any way I want between A and B, and regardless of what I pick for x, I can still pick y any way I want between C and D. So this is not a rectangle, this is a rectangle. So we have this important idea of kind of independence between the two variables. Okay, and we saw in this case, we have a little domain or a domain D here, and we have a little chunk of the domain. This domain represents an area that we're integrating over, and we're integrating some function that has a height above that. So we're getting something like a volume out of there. The little chunk of area over which we might integrate in a Riemann box looks like dx times dy. Why is that? Well, we have some increment in the x direction dx, some increment in the y direction dy, and that's why dA is dx times dy. The area of that little box, I mean, I kind of drew it as the whole rectangle here, but typically we think of this rectangle as being broken up into smaller ones, and each one of those small rectangles is going to be of area dx times dy. So that's our area increment. Now let's suppose that we wanted to, instead of using a coordinate system like rectangular or Cartesian coordinates, let's suppose that I had a region. Maybe this region is, if this is a circle or a quadrant of a circle, maybe this region is, say, a little slice of a circle. And maybe this is the domain I want to integrate over. And here I'll make it even a little bit more general. Instead of taking a slice of a circle, I'll take kind of I'll take a slice that is in between two circles. So this green circle is maybe a circle of radius r naught, and the blue one of radius r1. And this slice maybe starts at an angle theta naught and goes to the angle theta 1. Now, if I want to describe this domain, this region of integration in rectangular coordinates, I can kind of see that it's going to be pretty messy, right? I mean, it kind of appears that I have, depending on where I am on the x-axis, I have a different bottom function depending on where I am and a different top function depending on where I am. It seems like it's going to be pretty messy. Like I might have to actually break this into 3 separate domains to work with. That's going to be pretty messy. This isn't naturally set up very nicely to work with rectangular coordinates. However, this is, in a sense, a rectangle. In what sense is it a rectangle? Well, if I try to do like set of x, y, the criterion for the x, y coordinates is quite complicated. But what if I were to look at polar coordinates? What if I were to look at choosing, instead of choosing an X value and a Y value to give me a certain point in the two-dimensional plane. If I were to choose a certain radial distance away from the origin and a certain angle of inclination, maybe something like that, from the x-axis, that also uniquely determines a point in the 2D plane. So over here, we looked at what are the admissible x's and y's, and we saw that when we had this kind of feeling of independence, that I can pick x freely and y freely, and they don't impact one another, unlike here, where picking x a certain way impacts what's allowed to be picked for y. But if I can pick both freely, that has that rectangular feel, and that made integration work pretty nicely. What are my constraints on r and theta here? Well, I see that regardless of theta, regardless of the angle that I'm interested in, what color can I use here? I guess I'll use black. So if I pick whatever theta I want, I can choose an r anywhere between r0 and r1. And independently of that, if I were to look at, say, picking some value for r, if I were to choose my value for r, that doesn't place any restriction on what I can choose for theta. If I wanted r to be, say, right in the middle of r0 and r1, I could pick any value of theta between theta naught and theta 1 still. So this is, in some sense, like a polar rectangle. From the perspective of polar coordinates, if we're kind of sweeping out a slice of a circle, or even kind of a part of a slice of a circle in this manner, the slice between two circles, that's effectively a polar rectangle. So in other words, the double integral over the domain of something, let's just call it f, dA, we could maybe write that as the double integral x goes from a to b, y goes from c to d, something like f of x, y, dy dx, in a situation like this over here, where that's kind of a nice way to write the integral. But if I was in a situation like I am over here, I might instead want to write something like the double integral as r goes from, or let me write it the other way. It's a little more typical to see it the other way. As theta goes from theta naught to theta 1, and r goes from r naught to r1 of, and I'll say something like g of r theta here, because the function will look different if we switch between coordinate systems. And then here we really feel like writing dr d theta. Let's double check though, is this the right thing to write? So what needs to go here is dA, a little increment of area. Over here, dA was dx times dy, just kind of in a sense the product of the two variables, differentials. But let's look at this little chunk of area. If I've already written quite a bit on this, let me just kind of redraw this. Not the prettiest drawing, but this is our domain of interest. It looks a little more actual rectangular than it should. So here, if I take an angle increment, d theta, and a radial increment, dr, what's kind of the approximate area of this slice that's stuck between these two circles? Well, this is approximately an actual rectangle where one side is dr, but note that the other side is not just d theta. Even if theta is in radians, this circular segment here, this arc here, is not just d theta. Of course it can't be, right? Because I could have a really big circle where, 1 degree change in theta, or a 0.1 radian or something change in theta, it sweeps out a large distance. Or I could have a really small circle, a small radius, where a small change in theta sweeps out a small radius. What is this radius here? It's approximately r d theta. So, right, because the circumference of the circle is 2 pi r, and d theta is just the proportion of 2 pi that we're going around the circle. So this circular segment here is r d theta. So very important that we note that that r has to be multiplied by d theta. So my little chunk of area then, dA, is going to look like r dr d theta. Really easy to forget this r there at first, but if you do this a few times, you'll see that, I think you'll get used to it, and you'll see that actually sometimes this r even comes in handy. We'll see a couple instances of that today, I think. So this is the benefit. If I see that I have a region of integration that seems to work pretty well under rectangular coordinates, if I can describe that region easily under the xy coordinate system, then I just kind of go that route maybe. But on the other hand, if I have a region of integration that seems very kind of circularly symmetric, that seems like I could describe it better or more easily in polar coordinates, maybe I want to use a system like this where I can get a nice setup for my integration instead of having something that's really complicated where, y goes from some crazy function of x to some other crazy function of x, and then I have to integrate x between two numbers. I might be able to get a kind of rectangular, in a sense, iterated integral if I move over to the polar coordinate system. So that's one use. And the other use is sometimes my integrand, the thing I'm integrating, maybe it's not super easy to integrate when I talk about it in terms of x and y, but maybe when I either rewrite it in terms of r and theta, or when I have this extra factor of r here, maybe my integrand becomes easier to integrate. So those are two reasons that we might want to switch from rectangular to polar coordinate system. Okay. So let's look at a couple of integrals over, in a sense, rectangular regions, but in the polar sense. So here we want to compute double integral over d, x plus y dA, where d is the set xy, where x squared plus y squared is between 4 and 16. So we note that x squared plus y squared equals 4 is the circle centered at the origin, radius 2, x squared plus y squared equals 16, circle centered at the origin, radius 4. And despite my kind of lopsided drawing, we can, I think, see that this is an annulus. It's the area between two circles with the same origin. And I suppose I could maybe describe this in terms of x and y, but we see that it's going to be pretty complicated, right? I mean, kind of here, closer to x equals 0, we have a top and a bottom function that are the circles, and or the inner circle and the outer circle, and further out, at x equals 3, it's kind of the top and bottom halves of the big circle. It's not going to be super easy to represent this in terms of X and Y. Maybe we could do it. Maybe we could force it to work, but right, this definitely has that circularly symmetric feel to it. So can I represent this in terms of R and theta instead? So here I have some theta and some R. I should have drawn that line a little shorter for a given point that is in our domain. I actually see pretty nicely here, no matter what choice I pick for theta, for any theta, R ranges between 2 and 4. I could pick R any way that I like between 2 and 4, regardless of what direction I'm looking at. And if I were to pick R to be some number between 2 and 4, maybe 3 or maybe 2.5, I could pick theta any way that I like. That whole circle of whatever radius between 2 and 4 is included in this domain. So for any R between 2 and 4, any of these R's, I can pick theta anyway, anywhere between 0 and 2 pi. So if I let theta range from 0 to 2 pi, that brings me all the way around the circle. And if I let R range from 2 to 4 for each of those thetas, that also describes this whole domain here, D. I want to be careful that that I get these right. You know, if I was dealing with, say, just the part in the first quadrant or something, I would restrict theta to be, say, 0 to pi over 2 instead of 2 pi. Not necessarily always going around for every region of integration, but in this one we are going all the way around. So theta goes from 0 to 2 pi and R from 2 to 4. Okay, so I would like to integrate with respect to theta and R, theta going from 0 to 2 pi, R going from 2 to 4. And now I need to do two things. The first thing I need to do is remember that dA, an increment of area in polar coordinates, we've done this change of variables. We can't just make it dr d theta, as tempting as that is. We need r dr d theta. So this whole thing, the r dr d theta, is all kind of taking the place of the just dy dx or dx dy that we had before. Now, the second thing, of course, I can't just do x plus y here. I'm trying to integrate with respect to r and theta. So I've rewritten my region in terms of r and theta. That's kind of the hard part usually. But I also have to rewrite my integrand in terms of r and theta. And for this, of course, I just use x equals r cos theta, y equals r sine theta. And since we're just doing x plus y, that makes this pretty easy. X just turns into r cos theta, and y into r sine theta. Okay, and now we can approach this a couple different ways, I suppose. We could integrate the whole thing with respect to r, and then with respect to theta. We could also recognize that actually this integrand, including the r now in the integrand, because it needs to get integrated as well. So it's kind of re-lumping that using the associative property. I see that this integrand is just r squared times cos theta plus sine theta, or just a function of r times a function of theta. Just like the idea in rectangular coordinates, where if I have, say, f of xy was g of x times h of y, I could kind of pull these two integrals apart, right? Basically, the g of x can come outside of the inner y integral, and then the inner y integral, what's left over, integral y equals c to d of h of y dy, that whole thing is just a number that can come all the way out of the x integral. So we can do something similar here. We could integrate theta equals 0 to 2 pi of the theta bit. And multiply by integral r equals 2 to 4 of the r bit. Now, very important, if we had something like, for some reason, like cosine of r times theta, we wouldn't be able to do this, right? It's only because we can write that whole integrand, including, of course, this little r here, as function of r times function of theta. And then essentially what we're doing is we're arguing that cos theta plus sine theta is a constant in r, so it comes out in front of the r integral, leaving us with an integral with respect to theta of something, some function of theta on the outside, but then times integral r equals 2 to 4 of r squared dr. But integral r equals 2 to 4 of r squared dr is just a constant. It's an actual, it's just a number. It's a definite integral with one variable. So that number can just come all the way outside of the theta integral like this. So the same reasoning as before. And here we see we get r cubed over 3 evaluated from 2 to 4 for the second integral. Or this gives me, well, what? 4 cubed is 64 minus 8 over 3. My first integral, actually, well, integral 0 to 2 pi of cos theta plus sine theta. Well, on 0 to 2 pi, cos and sine are both 2 pi periodic. They both have as much area above the independent variable axis as below it. So this whole thing actually zeroes out, ends up being 0. So strictly speaking, we could have gotten away without doing the r integral, but wasn't difficult to do it. Doesn't make sense that this should zero out. So let's consider this region here. It has this nice circular symmetry to it. And what are we integrating? We're integrating x plus y. Well, if I pick, say, a point in the first quadrant up here, this has some positive x and some positive y. But there's a corresponding point in the third quadrant that has exactly the negative of that, right? Where the x changes to negative x, the y changes to negative y. That has exactly the opposite contribution, that kind of little contribution to volume that's really kind of signed volume is exactly the opposite. And same thing if we picked something in the second quadrant, there will be one in the fourth quadrant with exactly the opposite signs. X negative, y positive will turn into x positive, y negative. So I think it is sensible that when we see this symmetry here and we think about it for a minute, we realize that, okay, that makes sense that this zeroes out. Are there any questions on this so far? Okay, let's look at the next example. So up here, this was just some integral of some function over some region. We could interpret that as a volume, or we could set up a volume problem as a type of integral. So I want to find the volume of the solid obtained by intersecting the upper half ball. So ball is like a fill-in sphere, z between 0 and root 16 minus x squared minus y squared. with the cylinder, x squared plus y squared less than or equal to 4. So what do we have going on here? Let's draw a picture first. Well, the upper half ball is of radius 4. So it has a cross section in the xy plane that looks like that. And this is 4, that's 4. And it kind of comes up to height 4. Like this. So my ball is a little dented, I suppose, but you get the idea. And so this is a solid, it's the upper half ball. And I want to look at a cylinder, x squared plus y squared less than or equal to 4. The intersection of those two solids is the one that I'm interested in. The projection of the cylinder on the xy plane is a circle of radius 2. And z is free here, so we can just move this circle up and down. So it's a little hard to see, but basically what we have is a little chunk of cylinder with kind of like a hemispherical type of like cap on top of it. So that's the volume we're interested in. Again, setting this up in XY coordinates, maybe we could do it, but it might be a hassle to do. We see that our domain our region of integration is just going to be this circle of radius 2. And our integrand, our height for our top of our volume, the bottom of our volume is just the xy plane, so we don't have to deal with anything more complicated on the bottom, but the top is this function here, 16 minus x squared minus y squared. So I could try to integrate root 16 minus x squared minus y squared dx dy, where x goes from something to something and y goes from something to something. The bounds on x, the inner bounds on x are going to be kind of complicated. The integrand isn't going to be super nice to do. So I noticed that that integral is not going to be easy to do. Not even easy relative to a Calc 3 problem, right? I mean, I guess nothing in Calc 3 is really easy, but it's not even going to be easy to do relative to Calc 3. But I, of course, noticed the nice circular symmetry of my domain. And I might ask myself really quickly, well, if I went to polar coordinates, what does my integrand look like? Does my integrand get terribly complicated, in which case I might just have to bite the bullet and do it in xy? But in this case, my integrand, well, this is just r squared, of course, is x squared plus y squared. This is just 16 minus r squared for the integrand. So the integrand really doesn't get any more complicated. In fact, it seems to get even simpler. And we can rewrite the domain pretty easily in polar coordinates. So switching to polar instead, or I guess using polar instead, I want to integrate my integrand, but in terms of r and theta. Now this can be kind of an annoying integral to do, right? We need a trig substitution and all that. But again, remember, we get r dr d theta. This actually makes this a very easy integral to do. That extra factor of r, we just have to do a basic substitution now. So one part of the change of variables is reframing the integrand in terms of r and theta instead of x and y. The other part is reframing the region in a polar manner. So I noticed that for any theta going around here, for any angle that I pick, r can range anywhere from 0 to 2. So for any theta, r can go between 0 and 2. And for any r, and when I say any, I mean any that, any theta between 0 and 2 pi, or when I say any r, I mean any r that is between 0 and 2, which we've found its range now. For any of these r's, if I pick this r, I can still pick theta any way that I want. It's not like I have, something like this where it's like, well, if I pick r here, I can't pick theta over this direction or something. Nothing like that. For any r between 0 and 2, I can pick theta any way that I want. And again, in this case, we're using a whole circle. We go all the way around 0 to 2 pi. And if we wanted to, we could split these two integrals apart. I'll do them in an iterated fashion just to show the other way of doing it. So here, if I have 16 minus r squared to the 1/2 power, that integral is going to look like 16 minus r squared to the 3/2 power times 2/3. It's going to look like that more or less. If I differentiate this, I get 3/2 times 2/3. That goes away. 16 minus r squared to the 1/2. That looks good. Chain rule pops out a minus 2r. I just have an r, so I also need a minus 1/2 to fix that. I think for simple substitutions, this is the easiest way to do it, kind of a guess and check approach. You kind of guess the general form, and then you just make the constants work out. So that takes care of this. And then, of course, r goes from 0 to 2, integrating all of this d theta. So this constant nets out to a minus 1/3. I've gotten rid of this, pulled all that out front. 16 minus r squared to the 3/2. So that's 16 minus 4 is 12 to the 3/2 power, minus this evaluated at 0, minus 16 to the 3/2 power d theta. Now, this isn't the nicest constant in the world, but it is just an integral of a constant d theta. This is just 2 pi minus 0 times minus 1/3 times, and we can simplify this a bit. So we want to square root and then cube. So 12 to the 3/2. If we square root 12, we get 12 is 4 times 3. We get 2 root 3 cubed, which gives me 8 times 3 times root 3, or that gives me 24 root 3. And then minus 16 to the 3/2, square rooting 16 is 4, and then we get 4 cubed is 64. So this looks to me like we get a 2 pi over 3 times 64 minus 24 root 3, probably a handful of other ways we could write that, but I don't think any of them is going to be really substantially simpler than writing it this way. Any questions so far? Okay, so these couple examples were integrals over, in a sense, rectangular regions in the polar view. So either circles in these cases, or even just slices of circles or slices of an annulus. Those kind of all qualify as rectangular regions where we can split the bounds of integration into bounds on theta and r that are independent of one another. There's no dependence between theta and r. Similar to how, again, up here in a actual rectangular region and rectangular coordinates, a domain like this, we can split x and y into bounds that are independent of each other. Whereas in something like this, we could choose maybe x freely between a and b, but once we choose x, that restricts our value for y. So then y depends on x, on which x we chose, or vice versa. If we chose y between c and d, our values for x would depend on which y we chose. So there's not an independence between the two choices in something like this triangular region here. So what if we want to do integrals over general regions in polar coordinates? What does that look like? So let's take this example. You might have done this in Calc 2. We could do this in Calc 2 in a different way, but we're going to look at a way of doing it in Calc 3 with a double integral. Find the area of one petal, so to speak, or leaf of this curve r equals 3 cos of 3 theta. So here we're taking theta to be between minus pi over 6 and plus pi over 6. But importantly, r now depends on theta. R ranges between 0 at the bottom end up to 3 cos of 3 theta. So once I choose theta, that affects what r's I'm allowed to choose. What does this curve look like? It's one of these kinds of curves. And in particular, this is one tracing of this petal or this leaf here. Okay, so when theta is 0, cos of 0 is 1, r is 3. So when theta is 0, I could choose r kind of anywhere between 0 and 3. But when theta is, say, up here at pi over 6 or down here at minus pi over 6 going the other way, well, then r is actually only allowed to be 0. That's the only r I could pick. And if I pick, say, an intermediate theta, maybe here, r could be some number between 0 and maybe, say, r equals 1 or something like that. So now r depends, the allowable r's depend on which theta we pick. So what is my integral going to look like? Well, the first thing, what's my integrand? I want an area. But a double integral kind of gives me a volume, right? And this might really annoy the physics and chemistry folks, but if I take a volume that is above, let me try to draw this in the x, y, z coordinate system. If I take a volume that is above this area, and if I just make it a volume that's of constant height 1 over that area, the numerical part of that volume will be the same as the numerical part of the area. Of course, the units won't match up, but we're doing math. We don't care about units. Kind of joking there, but we care about units sometimes, but not nearly as much as the physicists or chemists do. If units were important, we would be very careful with them. But in this case, the point is that the numerical value for the volume, if we just pick our surface height to be 1, if we just pick our surface of interest to be the plane, z equals 1, then the numerical value of that volume is just the same as the numerical value of the area. Of course, the units would be cube units instead of square units, but we can get away with something like this. So we want to integrate 1 dA and our double integral, and we integrate one either way, whether we're in polar or rectangular coordinates, same idea applies. Here we're using polar because this is a polar curve. It's much nicer to represent this as a function of r and theta than an x and y. Now, strictly speaking, I mean, so far I've done r dr d theta. Strictly speaking, I could do either r as the inner integral or theta as the inner integral. So I have to be strategic. But I do note here that r depends on theta, and theta is independent of r. So I do want to do the r integral as the inner integral. So r goes from 0 to 3 cos of 3 theta. And then theta goes from minus pi over 6 to pi over 6. And again, super important to remember that area increment is not just something like dr d theta, it's r dr d theta. It almost, like, once you do several of these, it almost is hard to say dr d theta without saying r dr d theta. Like that, just the r dr d theta just kind of like is like etched in your brain after a while. But it is something you have to consciously remember the first, 10 or 15 or something of these problems you do. Okay, so my inner integral is just, well, r dr. So that's 1/2 r squared. And I have my theta integral outside of that. Kind of as a side note, just a really quick side note, we might be tempted here to do something like try to pull this rdr integral out of the theta integral because, well, I mean, the integrand does not depend on theta, but note that the bound depends on theta. So the result of this integral with respect to r is going to have thetas in it. We cannot just pull this out of the theta integral. Just a little side note on that. So these integrals do have that dependency. It's not through the integrand, but it's through the bounds of integration on the inner integral. So when we integrate the r integral, that goes from r equals 0 to 3 cos of 3 theta, and then we have a d theta over here. Theta goes from minus pi over 6 to pi over 6. I have a 1/2. Let me just pull that out front. And then r squared is going to be 9 cos squared of 3 theta, and then minus 0. So just the d theta after that. One thing that I do notice here is in my theta integral, I have a bit of nice symmetry here. I'm integrating, this is just now a one-dimensional integral, so we're thinking back to single variable calc. I'm integrating an even function, cos squared of 3 theta, over a symmetric interval of integration, minus pi over 6 to pi over 6. No integration problems. This will integrate just fine. It's not like going to blow up to infinity or something. So we can use that symmetry and just say this is twice the integral from 0 to pi over 6. So this is twice the integral from 0 to pi over 6. That'll save us a little bit of arithmetic gymnastics later on. These go away. I get out in front a 9. And then if we remember how to integrate cosine to power or sine to power, if I had to say cosine cubed of 3 theta, I would probably pull off one of those cosines and make it a cosine squared times cosine theta, cosine 3 theta d theta. I would use that cosine that I pulled off as my kind of du for a substitution. And that would tell me that my u is going to look something like sine of 3 theta. So I'd get like u squared du from something like that. But if I have an even number of powers like I have here, I can't really do that. If I pull off a cosine to use as my du, I'm left with only a single cosine, and I can't use Pythagorean identity to switch that into a sine very easily. So the way that I approach this is I have a trig identity that cos squared theta. You can get this from a combination of Pythagorean identity and double angle identities. Cos squared theta. Let me actually write it as cos squared x equals 1/2 times, and it's either 1 plus or minus cosine of 2x. So the cos squared of x turns into one of the sines, and the sine squared of x turns into the other one. If you can't remember which way it goes, if you don't remember whether the cos squared goes with the plus or the minus and the sine squared goes with the plus or the minus, we'll just plug in x equals 0. Cos squared of 0 is 1. 1 plus, well, if I had 1 minus cos of 0, that would give me 0 on the right-hand side. That's got to be the one that's associated to sine, because sine of 0 is 0. This has got to be a plus to give me 1 plus 1 is 2 over 2 is indeed 1. Just match them up at the special case x equals 0, and you can figure out which plus or minus to put in association with which cos squared or sine squared. But anyway, we see that we need to integrate this with the case x equals 3 theta. So I have a 1/2 coming out. Theta still goes from 0 to pi over 6 because we did this little symmetry trick here to save a little arithmetic. And I have 1 plus cos of, cos of 2 times 3 theta, cos of 6 theta, d theta. We are in radians here, so, ending up with thetas that are outside of trig functions is perfectly fine, but we do want to make sure that we're working in radians and that we're not working in degrees. At this point, I think that's pretty standard this far into calc, but just a reminder on that. And then, of course, integrating cos of 6 theta integrates up to sine of 6 theta. When we differentiate, we get a factor of 6 popping out. We need a 1/6 to cancel that out. And I get 9/2 times pi over 6 plus 1/6 sine of 6 times pi over 6, but that's sine of pi, which is 0. So that's plus 0. And then minus, well, minus when theta is 0 is minus 0. And then minus 1/6 sine of 0 is 0. So altogether, we get this divides out and we get 3/4 pi. So the area of one petal or leaf of this function is 3/4 pi. Any questions on that? Okay, then moving down to example 4. Pretty interesting little example here. Find the area of the region bounded above by the spiral r equals pi over 3 theta and below by the origin, and then also between r equals 1 and r equals 2. So let's look at this spiral and get a little bit more of an idea of why the wording here kind of makes sense. Okay, so I have x and y for my axes, of course, but we're thinking in terms of r and theta. We see that as theta goes to 0, this kind of blows up. So let's think of thetas that are at the other end. Often we start at theta equals 0 and kind of increment our way around, but let's start at kind of theta equals 2 pi. And see what the values for r are. If I have something like 2 pi, well, pi over 3 theta is pi over 6 pi, that's 1/6. So that's kind of around here. Let's say this is maybe 1/6 is like when we're approaching the positive x-axis, but kind of from from the fourth quadrant. What about when we have 3 pi over 2, the negative y-axis? Well, 3 theta is going to be 9 pi over 2. 1 over 3 theta is going to be 2 over 9 pi, multiplied by pi is 2/9. 1/6 is about 0.17 or so. 2/9 is about 0.22. So we're getting a little farther away from the origin here. When theta equals pi at the negative x-axis, well, then we just have 1/3. That's an easy one to do. About 0.33, getting even a little further away from the origin. When theta is pi over 2, well, then 3 theta is 3 pi over 2. Pi over 3 theta is 2/3. Getting even a little farther away from the origin. Let me try to make these somewhat similar axis scales. And then what happens is as theta kind of works its way back to 0, r gets larger and larger and larger. So we have something like this kind of a deal. It almost reminds me of one of those little things you used to like poke into an iPhone to pop out the SIM card. I don't think you can remove the SIM card these days, but they used to give you a little thingy that was like a paper clip that kind of, it's like this, and you put your finger through this part and poke it in and get your SIM card out. It reminds me of one of those kind of devices. Okay, so if I have r equals 1 and r equals 2, oh, they still do that with Android. Somebody said in chat. Let me actually zoom in a little bit so I can draw this a little better. If I'm going between r equals 1 and r equals 2, it's really tempting to do something like this and say, oh, well, this is our domain. But this isn't quite right? This is thinking very much in like a rectangular coordinate way of thinking, but that's not really how our function or our region is really defined here. We're thinking of going from the origin, and we're thinking of r equals 1 and r equals 2 as being circles. So I have kind of this circular segment here for r equals 1 for the circle of radius 1, and another one for a circle of radius 2. So I am interested in the intersections here and here, but I'm kind of interested in going from the origin out to this intersection where r equals 2, and going from the origin out to this intersection r equals 1. So actually and I'm looking for between r equals 1 and r equals 2. So this is going to be kind of my lower bound in a sense. Let me actually draw that in red so it's a little easier to see differently. So between r equals 1 and r equals 2, I don't ever want to be closer to the origin r equals 1. So I'm not including this little kind of semi-triangle type slice here. My region of integration, my domain D, is this kind of funny shape here. That top part looks like it's just a horizontal line at like, y equals 2/3 or something, but it's really not. It's this kind of crazy spiral thing. And then my left bound is actually a little circular arc. So even though this looks like it could be it looks like close to a triangle if you just look at it visually, it's really not a triangle. It's something that would be pretty messy to try to set up the bounds in the XY coordinate system. So of course we're using r theta. Okay. So if I look at this, what do I see? Well, I see as I increment theta, that restricts the r's that I could choose. If theta is kind of near this upper angle here, then r has to stay very close to 1. If theta is more towards the lower angle, r can range anywhere more or less between 1 and 2. if I choose r a certain way, if I chose r to be a number quite close to 2, that very much restricts what thetas I can be talking about. So how might I want to approach this? Well, between r equals 1 and r equals 2 is kind of a super nice bound. I would like to work with this and then say, how does theta depend on the r's that I chose? Well, let's first figure out what are my two possible thetas here. Well, I'm running out of different colors to use, but I'll just keep using black over here. When r equals 1, well, I know that r equals pi over 3 theta is the same as saying theta is pi over 3r. So when r equals 1, theta equals pi over 3. And when r equals 2 on this spiral here, this point of intersection on the spiral, theta equals pi over 6. Okay, so let me actually zoom in a little further. So what I'm thinking of here is, let me see if I can get a different color. Not really. Maybe I'll use black again. So what I'm thinking of here is that r is going to go between 1 and 2, and what is theta going to look like? If I pick a certain r, let's say some r naught here, some arbitrary radius r that I'm interested in, what can the range of theta be? It can go from here to here. In other words, the range of theta is going to be from this kind of lower theta, the theta associated with r equals 2, it's going to be from pi over 6. We can always we always start at pi over 6 and then go counterclockwise until we run into the intersection of that particular r that we chose with that spiral. And then we go up to, well, for the r that we chose, that theta where we have to stop, where we intersect the spiral at that r, is pi over 3r. I just got that by solving r equals pi over 3 theta for theta. So theta starts at pi over 6, that kind of lower blue curve or blue straight line, and then goes counterclockwise until it hits that point of intersection between the spiral and that circle with radius r naught. That's when we stop incrementing theta. And of course, if we chose a smaller value for r naught, we will be able to use a wider range of thetas, and a larger value for r naught, a narrower range of thetas, because this pi over 3r is either further away or closer to pi over 6. Okay, now nicely enough, I mean, this was a lot of work to get this set up, but now it's not that difficult to do. So from this point forward, I have my double integral. Well, again, I'm just looking for an area of a 2D region. I'm just going to integrate 1. dA is just r dr d theta, as it always is. That part never changes. As long as we're in polar coordinates, that dA is always r dr d theta. Now here, note that I have theta as a function of r, and r kind of acting somewhat independently of theta, but theta is dependent on r. So actually, in this case, I want to just switch my order of integration. I'm going to integrate d theta dr. Doesn't really roll off the tongue, r d theta dr, but I'm going to just switch these two. I'm going to integrate theta as my inner integral. Theta is going to go from pi over 6 to pi over 3r, and then r is going to go from 1 to 2. And just like before, I mean, I can factor the r in the integrand out of the theta integral, no problem there, but I can't pull the two integrals apart completely because the theta integral, its upper bound depends on r, and that needs to be taken into account in the r integral. So I've pulled the r out front here. And then, of course, just integrating 1d theta between two bounds is just the difference between those two bounds. Or, oops, so used to doing theta last that it's almost just second nature to write it. Okay, if I multiply through it, by the way, it's super easy to kind of forget this r floating around on occasion. So if you're going through and you enter an answer into WebAssign or something and it's not matching up, take a look and see if you left this r behind. It's really easy to kind of forget about it and just integrate this stuff with respect to r or something. But first, we're going to distribute. We get a pi over 3 minus pi over 6r, integrating that dr. This, of course, gives me pi over 3 times 2 minus 1. That's just a constant integrated over that interval. And then minus pi over 12 r squared from 1 to 2. This gives me pi over 3, and then minus pi over 12 times 4, and then minus a minus, so plus pi over 12 times 1. Well, pi over 12 times 4 is pi over 3. These guys go away. And we get pi over 12. This would be a pretty nasty problem to try to work out in rectangular coordinates, but in polar coordinates, not too bad. The biggest difficulty was really, number one, changing our kind of mental default perspective to think of this verbal definition of this region as defining a polar region rather than a rectangular region, not getting tied into things like above or below, meaning with respect to the x and y axes, but with respect to kind of the origin and radial distance and so on. And then the second thing, just being really careful with all of our details down here, just making sure we get all of our bounds of integration set up correctly, and that we get the dA set up correctly, all of that. Any questions on this? Okay. I think I'd like to skip to the next one. I want to get to example 6 because it's kind of an interesting example, pretty standard example to do, and then come back to example 5. Example 5 just has a lot of kind of arithmetic to work through. So if we don't get quite through all the arithmetic, I'm not super worried about it. But I want to make sure we get through example 6. So example 6, use a double integral in polar coordinates to evaluate this single variable integral minus infinity to infinity e to the minus x squared dx. Now, one little note here, I'm going to be a little hand wavy on some of these details. We know when we start throwing around infinities, we have improper integrals. That always means there's some kind of limit. Typically, we'd have to be very careful. All of those like little very careful things we have to take into account do work out fine for this problem. This is integrable and everything, no problems there. But I just don't want to get into all those nitty-gritty details here. But this is actually quite an important function to kind of understand how it works. This e to the minus x squared function, this relates to the normal distribution, to the error function. It's used a ton in statistics. It's used a lot in engineering. So these kind of e to the minus x squared type functions are really important to understand. And we're going to see that not only is this integrable, but we'll be able to figure out the value of the integral. And from that, we can figure out integrals like this one, for instance, the integral of the standard normal distribution, or the integral of a general normal distribution with two parameters, mu and sigma. Mu is the mean or kind of the average, and sigma, the standard deviation, or kind of the spread. And so the exercise down here is to use this result that we're going to show to show each of these. And I wouldn't recommend setting up these integrals from first principles. I mean, you could do it for this one. This one would probably be pretty messy, but use the result that we are going to show, and then use a change of variables, use a substitution to bring these two questions back into something that can be reframed this way. Use a substitution, make it look like e to the minus u squared du, integrated from minus infinity to infinity, and then get your answer that way. So this is more of a Calc 1 exercise, not a repetition of what we're going to do here. Okay, so let's take a look at this. Let me actually first get myself a little more room up here, because when I enter to get more space, it doesn't move my my drawing. So, all right, so let's take a look at this integral. We're going to name it I. And if I look at this, it doesn't look like a polar coordinate integral as it is. It's just, first of all, it's a single integral, not a double integral. And second, I don't really see anything that looks like a circle or anything like that. But if I look a little closer, and if I'm a little bit less strict with my interpretation, I say, well, I mean, that x squared, I know in polar coordinates, r squared is an important idea. And r squared is x squared plus y squared. That's really the idea that I'm going to leverage here. So I squared is the integral times itself. But in this second integral, I mean, there's nothing, this x is just a dummy variable, right? It's just a dummy variable of integration. I would get the same answer here. I get the same value if I used, you know, z integral minus infinity to infinity of e minus z squared dz, or if I used w squared dw, or whatever. So this is just the value of this integral. This is just some number times itself. So that's I squared. But I kind of noticed that, and this is where the hand wavy part comes in, if I have two kind of independent integrals in double integral world, I mean, if I have a double integral that has that independence property, I can split it out into two independent integrals. Well, I could do that in reverse. I could combine them together under a single double integral. Kind of a weird way to say it, a single double integral. Now, I mean, again, you might balk at this and say, oh, well, when we're doing minus infinity to infinity, does that mess up things? I mean, if we were just doing minus 1 to 1 for both of them, maybe it would work. Well, in this case, it works just fine. But again, that's the annoying details that we're going to just hand wave our way past. And then what do I see here? Well, I see that this is the double integral, really over R2, over the entire two-dimensional plane, right? Well, exponential functions, I have the same base to different exponents. I can just add the exponents. Minus x squared minus y squared, or I'm going to do plus y squared and put it in parentheses. dA. I can abstract away from the rectangular coordinate system a little bit and write it this way, where this guy just became dA, and these bounds are clearly just ranging over all of R2. But now what if I want to reinterpret this in polar coordinates? We'll think about what theta and r will be in a minute, the bounds. But I notice that this is just e to the minus r squared. And you might say to yourself, well, what the heck did we get? We just went through all of this work to get the same blasted thing that we can't integrate in the first place, right? As an aside, I mean, I think we all remember this, but if you don't remember from Calc 1 and Calc 2, this is a function that we can't just easily integrate. So you might say, well, what did this get me? I did all of this work to just get the same thing that I had up here. But the magic is, what is the A? R dr d theta. Now, r e to the minus r squared, that is an integrand that I can integrate pretty easily, just a basic substitution. I couldn't do a substitution up here because I want to do something like u equals x squared, but du then looks like x dx, and I don't have another x down here that I can kind of borrow for that du. That's not there. But I do have this extra variable factor here that I can borrow to make a du now. On R2, of course, theta can go from 0 to 2 pi, and r can go from 0 to infinity. I see that this is a quote rectangular region in the sense that the bounds on theta and the bounds on r do not depend on, neither one depends on the other. I see that this is actually, from theta's perspective, the integral of a constant d theta. That whole integral r equals 0 to infinity, e to the minus r squared, r dr. That whole thing is just a number, it's just a constant. So this is just 2 pi minus 0 times that constant. And that constant, well, I'd like it to look something like e to the minus r squared. If I differentiate that, I get e to the minus r squared times negative 2r. I need a negative 1/2 to fix that. And I do now have my factor of r, that all-important factor of r that I need to make the substitution work out. And evaluating from r equals 0 to infinity. So this is negative pi. E to the minus infinity is r goes to infinity, minus r squared goes to minus infinity. E to the negative infinity is 0, minus e to the 0 is 1. Or this is just pi. Now that's I squared is pi. So then my integral has to be root pi. Okay, any questions on this one? So this is a very important integral. It's kind of the basis for a lot of work in normal distributions and so on. And it's important to know because we want to, in say a normal distribution like this, we want to set the distribution up so that kind of fundamentally it has kind of a total area under it of 1 and not some arbitrary number. And so it's important to know that this is the thing that we need to divide by to get an area under the curve of 1, right? If this integral is sigma root 2 pi, then the integral of this function over sigma root 2 pi is 1, and that's one of our criteria that we that's an important criterion in stats. Okay, so now looking back
I have a question.
Yeah, sure.
Can you just go over how you got the negative 1/2 in front of the e to the negative r squared?
Yeah, sure.
One more time, thank you.
So I want to find the antiderivative of r e to the minus r squared. Now I can do a substitution here, but I know that this is going to look like e to the minus r squared. It's going to look something like this. If I differentiate this, what do I get? Do I get this? Well, if I differentiate this, I get e to the minus r squared times negative 2r. That's almost what I have up here, but I have a factor of negative 2. So I fix this by making it, by multiplying by negative 1/2 in front. And now I do see that my derivative of negative 1/2 e to the minus r squared is r e to the negative r squared. You could also take kind of a more standardized approach where you say u equals negative r squared, du is negative 2r dr, but I have an r dr here without the negative 2, so negative 1/2 du is r dr. So r e to the negative r squared dr is e to the u, and then r dr is negative 1/2 du. So you could do that as well.
Okay, thank you.
Yeah, sure. Okay, so going back to example 5, here we want to compute the integral of this kind of crazy thing, x squared plus y squared to the minus 2, where uh, our region of integration is the upper right quarter circle of the circle with radius 1, centered at 1, 0. So that's our region of integration. We're centered at 1, 0, and our circle has radius 1. Okay, so in a sense, this is really kind of screaming for polar coordinates. Number one, x squared plus y squared makes r squared, and that's going to be a lot easier to work with. Instead of dealing with 1 over x squared plus y squared squared, we'll be dealing with 1 over r to the 4th. That seems like it's going to go a lot better. And we have a circle in play here. But on the other hand, it's not a circle centered at the origin, so it's not super simple to get its polar representation. So let's look at this as a polar function. So we're looking at a certain angle. We have two choices for r. We have an upper and a lower bound for r, and we can choose r between those numbers for a given theta. And I see that the red curve is the lower bound for r. And maybe I'll make this a blue curve. The blue curve is the upper bound for r. So the vertical line, x equals 1, is the lower bound for r. So the lower bound for r is x equals 1. But in polar coordinates, x equals r cos theta, or r is then secant theta. So that's our lower bound for r. And then our upper bound for r is a bit tedious to work out. You can use the rectangular coordinate system definition for the circle. It's x minus 1 all squared plus y squared equals 1. Plug in x equals r cos theta and y equals r sine theta. A bunch of stuff will cancel. You'll be able to divide out a factor of r, and you'll get what ends up being r equals 2 cosine of theta for the upper bound for r. So for a given theta, r is going to go from r equals secant theta up to r equals 2 cos theta. And then what is theta going to range from? Well, of course, the lower bound for theta is when we're right along the x-axis, when theta is 0. And the upper bound is when we have our radial line just hitting that intersection of this x equals 1 line with the top half of the circle. And here I note that my horizontal distance is 1 unit. My vertical distance is 1 unit. this is a 45, 45, 90 triangle, or an angle of pi over 4. If I go any steeper or any more counterclockwise than pi over 4, then there are no points in the domain at that angle. So theta sweeps out from 0 to pi over 4, and for a given theta, r goes between this lower and upper bound. Okay, so I want to compute the double integral. Well, x squared plus y squared, remember now we're in polar coordinates, is r squared. R squared to the -2 is r to the -4. dA is r dr d theta. And now theta is the one that's kind of independent of r, but r depends on theta. So I've got to do the r integral on the inside and then the theta on the outside. The lower bound is secant theta, and the upper bound is 2 cos theta. And then theta goes from 0 to pi over 4. And this is a fairly standard set of integration to do, so I'll leave this as an exercise since we are about out of time, but you should end up with pi over 16 after all of this. Just one little note maybe is that recall that the integral of secant squared is tangent. The derivative of tangent theta is secant squared theta. So if you see a secant squared theta popping out under the integral sign, integral of secant squared theta is tangent theta. And the second thing to remember is just be very careful with your signs down here. Easy to get them mixed up and mistakenly come up with like an r to the -5 or something from this, right? This is r to the -4 times r to the 1, so that's r to the -3, and we're integrating that. We're bumping the power up 1 to r to the -2. So a couple notes on that, but I'll leave that as an exercise. From this point forward, it's less about the polar integral and more about just being careful with antiderivatives and the arithmetic and the trig and all of that stuff.